Okay, so let's try some problems and stick some numbers into these equations. So with the help of some students of mine from last semester, here we have a problem. Starting from rest, Kaveh accelerates with a constant acceleration of 1.50 meters per second squared for 5.00 seconds. What is Kaveh's final speed and how far has he run after this time? Alright, so what we're going to do is start with this problem and we're going to translate it into a mathematical problem that we can then use our equations to solve. Let's go back to our equations. So here we have the four kinematic equations. Let's look at how many variables we're actually dealing with. We've got the initial position, x0, and the final position, x. We've got the initial velocity and the final velocity, v0 and v. We have the acceleration, a, and the time, t. So 1, 2, 3, 4, 5, 6. We've got 6 different variables, and you'll notice that those are all the variables that are involved in these 4 problems. So let's see if we can't work with these 6, figure out 3 things. What do we know? What do we not know, or what don't we know? And then, what do we want? What are we looking for? What are we trying to solve for? We don't necessarily have to solve for everything we don't know if the problem doesn't ask for it. So we'll only solve for those parts that the question is actually asking for. So, let's go back to the problem and let's look at this step by step. Starting from rest. Now what does that mean, starting from rest? Well, what it means is starting from no motion, starting from a point of not moving. So what does that tell us? Starting from rest means Kaveh's initial velocity is 0. v0 is 0. He accelerates with a constant acceleration of 1.50 meters per second squared. Okay, so that's what A is. And the fact that it's a constant acceleration tells us that we can use these 4 kinematic equations because we derived those equations under the assumption of constant acceleration. So that tells us that we can use those equations. So A is 1.5 meters per second squared for 5 seconds. Well, this doesn't even tell us what 5 seconds is, but the fact that it's got units of seconds tells us that it's a time, so that must be t. T is 5 seconds. What is Kaveh's final speed? Well, what are we looking for? Final speed, in other words, final velocity. If it's a positive, we're looking for v. And how far has he run after this time? This doesn't tell us what his initial position is, so we're free to choose our origin at the initial position. So we'll set x0 equal to 0. How far has he run after this time? Then what we're looking for is the position after the time t. In other words, we're looking for x. So this is great. We know v0 is 0, a is 1.50 meters per second squared, t is 5 seconds. What we're looking for is v and x, assuming we can set x0 equal to 0. Great. Let's go back to our variables. Alright, so what do we know? Well, let's start at the top and work our way down. x0, we know is 0. We can set that equal to 0. We're free to do that. v0, he starts from rest. We know v0 is equal to 0. The acceleration was 1.50 meters per second squared. And the time t, we know, was 5 seconds. Final position, we don't know that. Final velocity, we don't know that. So, we know what we know what we don't know. What do we want? Well, we're asked for how fast is he moving, what's the final speed, and how far has he run. So we're actually looking for the 2 quantities that we don't have. Alright, very good. One thing I did not do that is usually a good idea and something that I will tend to do whenever we solve a problem is the first thing to do is draw a picture. Now, it's a little hard for me to do that when I'm flipping back and forth between the overhead and the screen, so let's do that now. What we've got is a very simple picture of someone that's starting to run. So we've got, Okay, there's Kaveh starting to run. Put the information on the drawing as you figure it out. So, Kaveh starts from rest. What does that tell us? Well, we could put right on the drawing v naught is equal to 0. Runs for 5 seconds, so we can say this takes 5 seconds. We've got an acceleration of 1.50, so we can put that right on the drawing. Put all that information from the problem right on the drawing, and then later on you can translate that back to the variables. It's always easier to start with a diagram. Students always ask me, or one thing they say is, they have a problem and they say, I don't know how to start this. I don't know even where to begin. This is where to begin. Begin with a drawing. You don't have to be an artist. A very simple sketch, what's going on, kind of helps you figure out physically what is happening in this problem. So there we go. Now, let's say we're at this point here. Let's go to our equations. What are we looking for? Well, the first thing we're asked for is the velocity or the speed, so v. Let's go to our equations and see what equation or equations could we use to find v. Now, let's do this step by step. Let's go to the first one. In order to use an equation to find what you're looking for, you have to have two things. You have to have an equation that involves the thing that you're looking for, and you have to know everything else in that equation in order to solve for the unknown. So, we're looking for v. We need an equation that has a v in it, and that only uses other values that we already know. We can't have something with an x in it because we don't know what x is. We wouldn't be able to put that in to solve for v. So let's go through this. Could we use equation number 1? Well, it has a v in it. Do we know everything else? Do we know v naught? Yes. Do we know a? Yes. Do we know t? Yes. So we could use equation number 1 and solve for v. Let's just go on and see if there's something else we could do. Number 2, does it have a v in it? Yeah. Do we know everything else? Well, no, because it's got an x in it and we don't know x. So we could not use this equation at this point to solve for v because we don't know x. What about 3? Does it have a v in it? No, it doesn't even have a v in it, so we couldn't use equation 3. Equation 4, it's got a v in it, but it also has an x in it, so we could not use equation 4. So what do? The only thing we can do is use equation 1 and use it to solve for v. So let's do that. We have that v is equal to v naught plus at. And now let's stick in the values. V naught is 0. A is 1.50 meters per second squared. And t is 5 seconds. So we have v is equal to 1.5 times 5, or 3 sig figs, 7.50. Notice 1 seconds, cancel one of the seconds in the denominator, and we end up with units of meters per second, which is just what we would expect for velocity. There we go. We now have the answer to the first half of the problem. V is 7.50 meters per second. Now, next part is, let's figure out what x is. Again, let's go back to our equations. Could we use equation number 1? No, it doesn't have an x in it. Could we use equation number 2? Yes, it has an x. Do we know everything else? Yes, we do. But let's hold on. Equation number 3, yes, it has an x, and yes, we know everything else. Equation number 4, yes, it has an x, and we know everything else. So we've got actually 3 choices. We could use equation number 2, 3, or 4. Would it be better to use one of those than the other? Is there something better is one equation better than the other in this particular problem? Well, the fact of the matter is I would say yes. And I would say that equation number 3 is better because 3 does not involve v. Equation 2 has a v in it, and equation 4 also has a v in it, but 3 does not. Now, why would we want to avoid using the value v? Well, v was not a term that was actually given to us in the statement of the problem. It was one that we actually had to calculate. If we made a mistake in our calculation, our value for v would be incorrect, and if we then used that, our value for x would also be incorrect. However, if we do not use v, we still have a chance of getting the right answer for x, if we don't use the incorrect value that we calculated for v. Hopefully we did correctly calculate v, but it's one way of avoiding compounding your mistake. So let's try and calculate x and not use the value for v. So in that case, we come to equation number 3. So let's do that. Equation number 3 is x equals x naught plus v naught t plus 1/2 at squared. X naught is 0. V naught is 0, so 0 times t, that's just going to give us 0. Plus 1/2 times a is 1.50 meters per second squared, t is 5 seconds squared. There we go. Multiply this out. Notice 3 sig figs. The 1/2, something I mentioned before, that is a term that came in from our definitions, and so we'll assume that it has as many significant figures as necessary. So we're multiplying quantities with 3 sig figs. Our answer will have 3 sig figs. And our final result is that x is equal to 18.8 meters. Multiply that out and make sure that you get the same result. And there we go. X is 18.8 meters. One last thing. Whenever you finish a problem, always look at your answers and ask yourself, do these answers make sense? Do they seem reasonable results? For example, Kavi's been running at 1.50 meters per second squared for 5 seconds. He's up to 7.5 meters per second. That seems, it's fast. He's running very fast, but that certainly seems reasonable. He's gone 18.8 meters. That seems like a reasonable distance to have run. So that certainly seems like, those certainly seem like reasonable answers for this problem. Okay, very good. Let's go on to the next problem. Okay, so here's another student of mine from last semester. While walking outside, Mohammed starts at 2.00 meters per second. During 1.50 seconds, he accelerates to 6.00 meters per second. How far does he walk during this time, and what is his acceleration? Something I mentioned last time, and let me mention it again. You won't always be told the initial velocity is this, the acceleration is this. Sometimes terms are just given in a problem. You ought to be able to figure out what type of quantity something is just by the units. So, for example, without even looking at anything else, 2 meters per second, what kind of a quantity is that? Well, the units are meters per second. We know that has to be a velocity. So that's going to be either the initial velocity or the final velocity. Well, it says Mohammed starts at that, so we know it's got to be the initial velocity. During 1.50 seconds, what is that? Well, seconds are a time. We know that has to be the time t. Accelerates to, what is this? Well, again, meters per second. That's got to be a velocity. Accelerates to that, so we already know the initial velocity. That's got to be the final velocity. So it's very easy, most of the time, to determine what the quantities are just by looking at the units, and then you can figure out is it initial or final value. All right, so let's go from here and let's work on this problem. Okay, so again, how do we start? Now, we don't have this problem written up, but hopefully you'll remember it, and I'll put the numbers down in a second. First thing to do, let's draw a picture. We've got Mohammed going out for a walk, so we've got him walking. Let's remember, while walking outside, Mohammed starts at 2 meters per second. So what does that tell us? We know his initial velocity is 2 meters per second. During 1.5 seconds, so we know this is going to take 1.5 seconds. He accelerates to 6 meters per second. So that's going to be his final velocity. How far does he walk during this time, and what is his acceleration? All right, so there we are. There's our picture. What do we do next? What's the next thing we do? First thing, draw a picture. Second thing, write down the variables. We already had those for the last problem. That's the next thing to always do for a problem. What are the variables? There are 6 of them. You can put them down any way you want. You don't have to solve problems like this I suggest that you do it this way because this is a simple, straightforward approach. If you just remember the steps, you'll be able to just figure out these problems. If you don't want to do this, sometimes people get confused, they don't know what to do next. Well, this is one methodical approach that you can use to solve the problems. What are the variables? If you remember them in this order, it will help you solve problems in the future. And I always will write them down in this order. X naught x, initial final position. V naught v, initial final velocity. A t, acceleration, time. So what do we know? X naught. X naught is the initial position. Unless you are told where something is, initially, in general, you can always assume the initial position is 0. So that's where we'll set our origin. We set our origin there. And typically we'll assume motion to the right is going to be in the positive direction, and that's where how I usually draw the pictures. If something is specifically stated different from that, you can always choose it the other way. All right, final position, we don't know that. Initial velocity, yeah, 2 meters per second. Final velocity, 6 meters per second. Acceleration, no, don't know that. Time, yeah, 1.50 seconds. There we go. Now, how far does he walk? We're looking for x. And what is his acceleration? We're looking for a. So, to start with, let's find x. So, back to what I said, what do we know? That's what we know. What do we not know? We don't know x. We don't know a. What are we looking for? What do we want? Well, we want the two things that we don't know. So let's find x first. Back to the equations. Let's find an equation that involves an x and only other things that we do know. Equation number 1, can we use that? No, it doesn't have an x in it. Equation number 2, could we use that? Yup, it's got an x and we know everything else. X naught, v naught v, and t. Equation number 3, could we use that? Well, it's got an x in it, but it's also got the acceleration in it, and we don't know the acceleration, so we cannot use number 3. Number 4, it's got an x in it, but it also has the acceleration which we don't know, so we cannot use equation number 4. So what equation do we use? Well, we have to use equation number 2. We figured out that's the only thing we can do. So, using equation number 2, x equals x naught plus 1/2 v naught plus v times t. What do we have? X naught is 0. 1/2 times v naught, which is 2 meters per second, plus v, which is 6 meters per second, times t, which is 1.50 seconds. There we go. Multiply those out. What do we get? Well, 2 plus 6 is 8, times 1/2 is 4. 4 times 1.5 is 6. Make sure I don't make any silly mistakes here. 6. X equals 6 meters. There we go. There's the answer to the first part of the problem. So we'll put this in here. 6 meters. Second part, what is the acceleration? So let's look. Number 1, can we use that for the acceleration? Well, it's got an a in it. Do we know everything else? Yes, we do. Number 2, could we use that? No, it doesn't have a in it. Number 3, we could use that. It's got an a in it, but it also has an x in it. And again, for the same reason as the last problem, let's avoid using that value if we can. So let's not use 3. Number 4, it's got an a in it, but it also has an x in it. So let's not use that. So what do we use? Let's use equation number 1. What do we have? V equals v naught plus a t. Let's solve that for a. Bring the v naught over here, divide by t. We have a equals v minus v naught over t. And let's put our numbers in. V is 6 meters per second. Minus v naught, which is 2 meters per second. Divided by t, which is 1.50 seconds. And what do we have? Notice we've got meters per second minus meters per second divided by seconds. That's going to give us a value in meters per second squared. 6 minus 2 is 4. 4 divided by 1.5 is 2.67. So we have an acceleration of 2.67 meters per second squared. And 3 sig figs again. There we go. So we've got the position, x, and the acceleration, a, and there we've solved that problem. Now, before we do another problem, I want to talk about, we have derived these for uniformly accelerated motion. I now want to talk about a specific kind of uniformly accelerated motion. In the late 1500s and early 1600s, Galileo Galilei was doing many experiments, and in particular some with objects falling under the influence of gravity. And what he developed was his law of falling bodies. And that states that in a vacuum, all bodies fall with the same acceleration. What I'd like to do is take a look at this and see what this means. So first, I have two objects here. One large object and one smaller object. And we're going to check to see what the accelerations of these two objects will be if I drop them under the influence of gravity. Now what I want you to do is to watch, but also listen and see if you can hear them fall. So here I've got the two objects. I'm going to hold them up here, and I'm going to drop them at the same time. Ready? 1, 2, 3. Now you might have noticed that they hit the ground very, very close to the same time. A large object and a small object both hit the ground at the same time. In other words, they both fell with the same acceleration. Now, why is it important that the law of falling bodies says in a vacuum? Well, because there are some objects that will not fall with the same acceleration. Here I have a balloon and a ball, and I'll drop these both at the same time, and we'll see what happens. Okay, obviously, they did not fall at with the same acceleration. The balloon fell with a smaller acceleration. The reason that we say in a vacuum is because we know that there is something called air resistance. And air resistance can slow things down. If we do not let things fall for too far, or too great a distance, or for too much time, and if they are not significantly different from each other, that air resistance will affect them very, very differently, then basically we can assume they will have the same acceleration. If the objects are very, very different, something very, very light, like this balloon, very, very large and light compared to this ball, the effective air resistance will be much more significant. But for many things, we can ignore the effective air resistance as long as we don't allow them to fall for too great a distance or for too much time. This allows us to look at a whole number of a new type of problem where objects fall under the influence of gravity. When an object falls only under the influence of gravity, we will assume that its acceleration is in a downward direction, and the value of that acceleration in metric units is 9.80 meters per second squared. The fact of the matter is that on different points of the Earth, the acceleration due to gravity is slightly different. So at the top of a mountain, it's slightly different than at the bottom of the mountain. At some points on the Earth, even at sea level, it can be slightly different at other points. And so this final digit sometimes varies. Sometimes you might see it quoted as 9.81, sometimes 9.80. For this course, I will use a value of 9.80. And please make sure that you use that also in your calculations so that I'll be able to tell if you've made any mistakes or something like that. We'll have consistent results. So we will assume a value of 9.80, and the symbol that is usually used for this is a lowercase g. So g is 9.80 meters per second squared. Don't put a minus sign in here. If you want to make the acceleration negative, in other words, if you choose your coordinate system to be positive upwards, then we'll say the acceleration is negative g. We won't stick the minus sign in here with our definition of g. We'll just say a is minus g. So There we go. G, 9.80 meters per second squared, the acceleration due to gravity, which is going to be in a downward direction when an object is moving only under the influence of gravity. So, let's try another problem.